Today, we want to find the volume of a pyramid. The pyramid has a base of 10 feet by 15 feet and a height of 8 feet. And I've attempted to draw my pyramid. I think I just kind of had the angle a little bit wrong. Yeah, it came out fine. It came out fine. Mainly, I wanted to highlight the red face that's kind of coming out of the page, and then that green face that kind of pushes back into the page. Because we're going to want to look at different views of this pyramid. Now, the important thing to note here is that we're not trying to solve some kind of mystery, like what is the volume of this pyramid, because we can just calculate that. We're just going to find the volume of the rectangular solid in which it sits. We'll just take 10 times 15 times 8. That's the volume of the rectangular solid from which we are cutting this pyramid. And we want 1/3 of that volume. So whatever that's going to be. I think I could take the 3 out of the 15. That's why I picked the 15. Originally, this was going to be 14. Then I'm like, oh, hang on, I need a 3. So 550 times 8, 400. It's not about finding the volume of a pyramid. It's about understanding how integration works. What we're going to do is we're going to look at horizontal slices, because we're trying to set up volume as cross-sectional area multiplied by height. I want to set up volume is area of the cross-section multiplied by height. This is what we're trying to set up in these problems. Area of the cross-section multiplied by height. What we have to remember is that the cross-sectional area can have variable size, but has to have a constant shape. We want something with a variable size and a constant shape. So if we try to slice this, say, front to back, so slice this front to back or from side to side, we won't have that constant shape. So like if we slice vertically, we'll have some kind of trapezoid shape. And if we slice a little bit further in, we'll have another trapezoid shape. But those trapezoids won't be similar, and that's the problem. Same thing happens if I slice parallel to this 15-foot side. So what we're going to do is we're going to slice horizontally so that every slice reveals a rectangle. We're going to slice horizontally for rectangular slices. We're going to slice parallel to the floor so that we always have a rectangle. The rectangles will get smaller, but we'll always have a rectangle. So the area that we're going to be using for our cross section is just length times width. Notice that it's not going to be 10 times 15. That's the width and the length just at the bottom. I'm talking about that pink slice part way up the pyramid. So I'm going to have a length and a width. I'm going to use that length and width for some small change in height. The sides are all angled, but I'm going to use this length times width, this area, and I'm going to assume my function is my area is constant for some small change in height, which I will not call delta H like I did yesterday. I'll call it delta X, even though I'm not using a capital H for the height. So the cross-sectional area is length times width times the height, which is delta X. So now our job is to write that length and the width as a function of some height, either the height above the base or the height from the top of the pyramid. Or if you know how I run a class at all, both. To define our X, let's look at two different views of this pyramid. So we're going to look at a couple of side views to help define X. One is going to be the side view from the front, looking at that 10-foot floor, the red facing. Scroll. So we're looking at the face with the 10. We got the height of 8. What we're looking at is the width. And we're going to take that width, even though the width is changing as the height goes from the floor up to the point, we're going to use that same width for some small change in X. So if we look at it from the other side, the 15-foot side, we've still got a height of 8. And this slice is still here, although now, when we look at this slice, we're seeing the length. We're still going to use this length for our volume calculation for some small change, delta x. So this is still delta x. This is still a height of 8. So there are the two side views. I need to write the length and the width in terms of some variable x. So that means we need to define something x. We have two reasonable choices, either from the bottom of the pyramid up to the slice or from the top of the pyramid down to the slice. It doesn't matter which one, but since we're going to predict that we're going to use similar triangles, I'm going to define x to be from the top of the pyramid down to the slice. Once we decide where x is going to go, we have made choices. So we have decided where 0 is. So up at the top here is where x equals 0. And then down here at the bottom is where x is equal to 8. And so this is the positive direction. Once you decide and label a variable, you have chosen where 0 goes, and you have chosen a positive direction. Once again, I chose x to be up here because I'm going to make a ratio. I'm going to use similar triangles. So I have x here. X is also going to be here. It's the same x. So we're going to make a ratio of the height to the base for both of these triangles. Take the height. Oh, I'm going to flip it over. I'm going to do the base to the height to do less algebraic gymnastics. So I'll take w over x will equal 10 over 8. Then over on the other side, I will set up L over x is 15 over 8. So from here, I can get expressions for the width and the length in terms of our delta variable x. That will give us a volume of the slice that's up entirely in terms of our delta variable x. We can put that together into a Riemann sum and then integrate. So W is 10/8 x. And L is 15/8 x. So the volume of the slice is going to be 15 over 8 times x times 10 over 8 x times delta x. Length times width times height. That's the volume of that little rectangular solid slice. And it's going to be a different volume depending on the value of x. At the top of the pyramid, the volume of that slice is 0. And that makes sense because x is at the top at 0. We plug in 0. At the bottom, when x is equal to 8, the area of that slice should be 10 times 15. So if I plug 8 into these expressions, the 8's cancel out, and I get 10 times 15. So in case you were wondering why I didn't simplify 10 over 8, that's why. Now this is the volume of the slice for all these different x values. So now we have to build a Riemann sum, which we skip over and just write down the total volume in a definite integral. I'm going to factor out the 15 over 8 and the 10 over 8, which I'm going to actually simplify now to 5 over 4. Now I'm just going to do, no, I'm not, 150 over 64. X squared. The delta x in the definite integral becomes a dx. Our discrete delta x becomes the continuous dx, and then we just integrate over all the values of x for which we have a slice. So we're going to have 150 over 64 times 1/3 x cubed evaluated from 0 to 8. So I'll have 150 over 64 times 1/3 times 8 cubed. And now you can see why I didn't bother simplifying it in skill. The 8 cubed cancels the 64, leaving an 8, and the 150 is clearly the 10 and the 15. So we end up with 1/3, 10 and 15 times 8. Just like we predicted. It's always good when your new process matches what you expect. Any questions? The point was not finding the volume of the pyramid. The point was setting up an integral and all the things that go into setting up the integral. I don't know if it happens as much anymore because we don't get to teach algebra anymore, but a very common refrain from people trying to learn algebra is once the problem is set up, I can do the math stuff. It's setting up the problem that's difficult. Which is true, perfectly valid observation. But setting up the problem is the point. Coming up with the answer is not. That's why the problems in algebra class are so patently ridiculous. A farmer is going to take 100 feet of fence and build a rectangular pen on the side of a river. Which makes me think that AI has been around a lot longer and we use it to write a bunch of math problems that don't make any freaking sense. This book has a great one. It has variable density. Silo is filled with sawdust and it's variable density. The density of the sawdust is 0 on the floor and it increases as we go up. So it's like anti-gravity sawdust. It's a great problem, clearly written by AI, because that's not how stuff works. So let's think about some variations on this theme. let's suppose that aliens come along and say, hey, that pyramid looks like a nice place to land, but it's all pointy at the top. So they just slice off the top 2 feet of the pyramid with, I don't know, lasers or something. So that they can land their spaceship, make a very impressive entrance. And I don't know, take over the world. So the good news is we don't have to do any more setup. All we've done is go from, let's say, this version. I'm just going to grab one of the sides because I don't need both for what I want to say. Do need too many details, I guess, but here we are. So here's the scenario we had before. It'd been nice to just copy and paste it. So what we're going to do is we're going to flatten this out, and we're not going to have to rebuild anything. That's the good news. So in this problem, the aliens come along and they cut off the top 2 feet. So this is now gone. And now we want the volume of what's left over. We want the volume of the truncated pyramid. I'm gonna put exclamation points everywhere because apparently this problem became much more dramatic in my mind while I was thinking about it. The good news is we don't have to do any more work. We had set up a definite integral where we just add up all the places, all the x values where we had pyramid. We just don't have any pyramid x equals 0 to x equals 2. So instead of integrating from 0 to 8, we'll just start integrating at 2 and integrate from 2 to 8. It was just an x squared dx. Where before we integrated all the x values where we had pyramid, we used to have pyramid starting at x equals 0 all the way down to 8. But instead of going from 0 to 8, we just truncate off the 2 feet from the top and integrate from 2 to 8. Now you might be thinking, we did this problem way back in geometry class. We'll just subtract the pyramid from the top from the whole pyramid. And yeah, we're doing the same thing here. Of course, all we do is we take the whole thing and subtract off the piece we're getting rid of to find out what's left. That's exactly what we're doing here. We're taking the pyramid with a height of 8 and subtracting off the pyramid with a height of 2. If all we had was geometry, we would have to figure out what the length and width are 2 feet down from the top of our pyramid. We can bypass all that and just integrate from 2 to 8. Integration takes care of all that for us. Any questions? It's not a flex for calculus to say, haha, look how good this is. You've saved yourself that calculation. That calculation is borderline trivial anyway. That's not the important thing. The important thing is the thinking that you apply here in calculus is the same thinking that you were working with back in geometry when you just cut a part off to figure out what's left. We're not trying to say that this is faster, because by the time we got to this point doing calculus, the other person has already figured out how much the top was and subtracted it from the 400 that we had for the whole thing. Speed is not the issue. Understanding how shit works, that's the issue. Then the aliens are like, oh, what's this calculus stuff? And then we're like, oh, you don't have this? And they're like, oh, no. Well, instead of destroying the earth, why don't we work together? And that's how calculus saved the earth. Notice I said the earth and not humanity. After we thought of calculus, they still wiped us all out. But the earth was good. Any questions? Comment? Snide remark? I'm going to emphasize that the answer isn't the important part. From a student standpoint, the answer is, of course, the important part. I would absolutely first look at this. If you're 400 minus something, whatever that is the correct 400 minus something. I'm saying, oh, this must have gone pretty well. Then I would look at your definite integral side. Ah, good. They just took the previous integral, integrated from 2 to 8 instead of from 0 to 8. I like it. The most common mistake that you're going to do here is integrate from 0 to 6, but that's not the bottom 6 feet of the pyramid. That's the top 6 feet of the pyramid. If we integrate from 0 to 6, that's going to be the top 6 feet of the pyramid, not the bottom 6 feet of the pyramid. How's everybody okay? alternate universe time. Really appreciate the MCU for giving us a much more widely known about multiverse idea. Because before the MCU, I was like, oh, all right, I have to refer to that Jet Li movie, and like not as many people have seen that as have seen like Doctor Strange and the Multiverse of Madness. So in some alternate universe, I forgot that I'm just going to use similar triangles to get the relationship between L and W and my variable, which I'm going to call Y, because in that alternate universe, instead of using X all the time, we use Y all the time. And so instead of X marked the spot, we're always asking Y. So I'm going to define Y to be the distance from the bottom of the pyramid up to the slice. So when we do that, down here at the bottom of the pyramid is 0, and up here at the top of the pyramid is 8. Now this is just fine. We just changed the direction of things, but I can't use similar triangles with Y. I have to use the other part. So at this point, I'm going, oh, we define Y from the bottom of the pyramid, but I need the top of the pyramid to make similar triangles. So what I need is this piece up here, 8 minus Y. So instead of setting up W over X is 10 over 8, I'm going to be setting up W over 8 minus Y is 10 over 8. Similarly, we're going to have to do this for the length as well. So in this alternate dimension or alternate universe, I've got my length. So we'll do the same thing for the length. The length will just be, oh, let me write this out. My length will be 15 over 8 times 8 minus Y. The width will be 10 over 8 times 8 minus Y times the height, which is delta Y. And this is what we're going to set up in our definite integral. In this case, we're integrating not from x equals 0 to x equals 8, but from y equals 0 to y equals 8. I know that sounded very similar, but in the previous setup, we did integrate it from the top to the bottom. Now we're integrating from the bottom to the top. So the V total will be from 0 to 8. All we're doing is making a simple substitution. Let x equal 8 minus y. Then dx is minus dy. And instead of going from 0 to 8, we go from 8 to 0. But it's got a negative, so we change the sign and go from 0 to 8. So this one substitutes into the previous one. And we already know it's going to be 400 anyway. What does change is if we do the truncated pyramid that the aliens got to. Because now in the truncated pyramid, we still chop off chop the height down to 6. But now since we're integrating from the bottom of the pyramid up, instead of integrating from 2 to 8, in this when x equals 2 to x equals 8 is the bottom 6 feet of the pyramid. Now the bottom of the 6 feet of the pyramid is y equals 0 to y equals 6. So here is where we integrate from 0 to 6. Questions? So there's a substitution for the second one. It just goes right into the first one. Remember, you have to integrate, you have to change your dy into a negative dx. That's going to put the 0 from 0 to 8 from 8 to 0, but the negative will change the order in which we integrate. Also, we have to change the endpoints. These are all y's in the second formulation. So when y is 0, x is 8. When y is 8, x is 0 because they go in opposite direction. And the one in the middle, when y is 6, x is equal to 2. We have an uncountable infinity of places we can define a variable. There are only 2 that make sense. They can all be substituted into each other. It's all just a yeah. Any questions? Comments? Brief thoughts? All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.